Let us start off the next session. Here we'll start off with autonomous robotics and electrified operations. We'll start off with the presentation given by Sergio. Sergio, the floor is yours.
Thank you and welcome everyone. Good morning. I'm here to present you the autonomous robotics and electrified operations for mines. And when you see the agenda, I'm very pleased to do this, and I'm very excited because I believe these 4 topics that we have gathered here for you are bringing one extremely interesting topic in the mine I/O. These technologies give you a vision of what a mine can be in the future. So we are going to go through them, and it's on our side, in your vision that you can build around it, that each one of them composed are doing for the mine in the present and in the future. So we are going to start with the optimizing mine operations workload scheduling and planning. I'm going to present electrification of mines through dynamic wireless charging, and we are going to see autonomous navigation in mining and robotics for fluided mines with our colleagues from the Mine I/O that I will present on each first at their presentation. So the first thing that we are going to present is from Tecnalia, a video that they have made for us specifically that is explaining the whole topic. So
I'm going to talk about task 3.5, the workload scheduling and planning. In this task, we have a developer planner which organizes the task, specifically when are they performed and what machine do them. The tasks are performed by different vehicles and machines, which they move from one location to another. So it's important the order in which the tasks are done. For instance, it's different if we do A, then B, then C, or if we do A, skip B, go to C, and then go back to B. The time that it takes this second order is longer than the first one. Also, some tasks need to be done before others. So there is a specific ordering. In the development cycle that is shown over here, so there are special tasks. For instance, haulage and loading has to happen at the same time, and the survey and blasting they don't need a vehicle, and blasting happens overnight between shifts. So we need to take in account all that. The input are the tasks or the locations where we have to do work, the vehicles available, and some restrictions that these vehicles, for the availability of these vehicles. We have just real locations, and the process is first we map all the locations with a digital map, compute the distance between all the different locations, pass all the input that we have to the engine that optimizes and obtains the result. It takes 30 minutes to optimize the 14 shifts within a week, and the result is the task vehicle assignment and the Gantt diagram. So the output is stored in a JSON format that can be shared with other computer applications. Here we can see a Gantt diagram saying what are the different tasks that are doing the vehicles. In black, we can see the periods when the vehicles is moving from one location to another. And in red, we can see when the vehicles are not available because of the restrictions. Here we can see how the curve of how the maximization process happens and how the cycles are maximized. The increment will obtain an increment of 5% compared to manual computations. This tool also serves in order to compute or to answer what if questions. For instance, if we want to do optimization considering different values for the restrictions. Thank you.
Great. So I hope this was a very short but very instructive video. We will have also online the support for the questions afterwards. So let's continue to the next topic, which brings us to my topic, electrification of mines through dynamic wireless charging. I'm Sergio Perez. My background is civil engineer. I made a PhD on pavements, and I'm working for Hendrix IPT, which is a Netherlands and German company specialized in wireless charging. So we are very strongly believing in wireless for mines because of the harsh environment. Wireless is the best way of bringing energy in such a situation. It has all the robustness needed. It can charge during operation. That means that we can really match the functionalities needed inside the mine. And it's really not having any safety issues with the electrification because you don't have open elements in the connectivities. And most important, I will say, any of the components that you might have in a mine will have any issue in safety, as there's no wear and tear. You don't have any sort of maintenance other than to be sure that the floor is kind of well adapted to continue driving. So in that sense, I need to make a very short point and parenthesis on how does it work. In our system, we have defined a 200 kilowatt energy transfer to the battery. We have a system that we call the 220 kilowatt charger because we have a 90% of efficiency. The most important element that I want you to take from here is that we have to be able to do wireless. We need 4 elements. The first element is what you do to transform the input energy into an energy that can be transferring through wireless. So you need to change the frequency of the AC current to 85 kilohertz. For that, you need also a coil that is going to make this field, and you're going to have the third element you need to have is another coil to receive it. And finally, very easy, you need to rectify this again. So there are 4 elements to be using a wireless. And in that sense, what you see here in the first part of the vehicle, you have 2 of the elements, is the electronics, what we call the track supply, and the second one, which is the primary coil. Sometimes you need a cooling, but for low heavy duty, like the mine one, you might not need it. So in the vehicle, you have the 2 other elements that are then the coil that is receiving and a rectifier. In itself, what you have, the components you see here, the first one in your left will be what we represent as the coil in the floor. The second one, the electronics. And then what we did in MineIO2 is that the third and the fourth component are in one only component. So the coil receiving and the rectifier is in one only component. And this is the important element because I'm going to show you the deliverables for MineIO. So also a small point in the concept. What we are proposing with the dynamic charging is that you will have some segments that will be put in on and off through the driving time of the vehicle. The first assessment that we did in the German mine was that the ramp is utilized by some trucks during 1 hour to go down and 1 hour to go up. So in that sense, you have a lot of time to utilize to charge, and you also have the opportunity next with the autonomous to just leave the truck go and charge while it's moving the goods or the materials and the truck itself downwards. So you see the concept was to use that in the ramp. That's what I'm just saying. And there we come to the 3 slides about the 3 components for the wireless. The first thing we did is in the ground assembly, we have an electronic, which is the heart of the whole technology. We are going to take the input from the grid and put it in 85 kilohertz to be able to transfer through the coil. You see some of the elements that were developed for these in a specific 200 kilowatt and the specifications of this cabinet, which is an extremely good achievement of the MineIO because we have been capable of bringing this equipment at a level of industrial equipment. You see the finishing of the equipment and it's what I will say almost the last stand. You could optimize the spaces, but in fact, this is the equipment. The second component I mentioned to you is the primary. What we call the primary in the ground assembly is the coil that is going to produce the magnetic field. In that sense, in 𝗏 we developed a design to position the cables in a way that the magnetic field will reach the efficiency that we are intending to. So at the end, what you see here in the tunnel will be with coils that are sinusoidal coils in 3 phases, providing the 85 kHz frequency for 200 kW that will be transferred to the vehicle while it moves. The last one of the deliverables, as I told you, we gather in one only equipment the rectification from this energy that's taken by the coils to be able to be transferred in DC power for the batteries. The beauty of the 𝗏 is that we reach the status on having also this equipment in an industrialized form, as you can see here in the picture. So more specifically about what we also did in the assessment of the mines in 𝗏. We took an example truck from the Björkal mine, and we went through the analysis on how we will be integrating these components that we have mentioned, and we did the simulation on the magnetic field, let's say, topology to assess what level of efficiency we have for different positions in the truck. So we could, in a real scale test, we could define for each truck where do we have to put it, to put this equipment to have the best efficiency. And on the other side, another assessment that was very important here is that I mentioned that this wireless has no troubles with dust, ice, and any sort of, let's say, material, but there is one material that might have an input or an effect in the field is the metallic elements. As we know, we were in a mine, a gold mine. We have the questions on how the material, the dust that can be around, can have any effect. So we did a test. We took material from the mine. We exposed it to hours of magnetic field, is what you see here in the bottom left picture. You see the coils. You see the coils that are getting warm. And when you go back to the material, you see that there's no warmth presenting in any part of this material. That means very quickly there's no losses that are happening there. That means very quickly that the magnetic field cannot be disturbed in a test, in factual. So of course our simulations were intending to go in that direction, but the test, I think it's important, and that's what we did in the frame of this project. So finally, I'm showing you our laboratory and how we did implement the movement of the receiver through the magnetic field, and we attest then the capability of battery simulator that we had in this laboratory, the reception of this 200 kilowatt charging capacity. You also see 1 or 2 pictures additional on our what we call peak rec, because it's a peak. It's peaking the energy and it's rectifying the energy. It's a name, smart name to keep everyone in head what it means. And finally, the test of the material. And also, let's say, of course, here, because we had a pilot that was intended for a mine that was not anymore in the project, we could not install in the TRL that we wanted. But 2 things I like to say. Maybe the laboratory you see here is TRL 4.5, but our equipments have been tested already in TRL 8. And the last picture that you saw is a first installation in a normal truck. So all the elements that we developed in 𝗏 are an industrial level, and just the pilot was shown as I just mentioned. So that brings the end of my presentation, and we are going to talk about autonomous navigation in mining. Christos Maliarakis is going to tell us about this. Christos, he works in Intelligence. He is the head of artificial intelligence and software engineering, and 𝗏 is specialized in robotics, UAV, and ground vehicles. So, Christos, please.
Thank you very much. Good morning, everyone. So, in this presentation, I will briefly present our work on autonomous navigation in mining, developed in the context of the 𝗏𝗏 project. The focus of our work was an advanced autonomous control and dynamic perception for complex underground environments where conditions are much more difficult than in normal outdoor driving. And we will see how this 𝗏𝗏 navigation algorithm that we developed was also integrated with a real vehicle developed from scratch from 𝗏𝗏 University. So the main goal of this task was to support autonomous and safe navigation for an electrified mining vehicle, because underground mining is a very challenging environment. So for this reason, we validated the solution on the 𝗏𝗏𝗃 research vehicle. There are a lot of reasons there are a lot of challenges underground. There is no GPS. The tunnel geometry is narrow and restrictive, and lighting conditions are poor. So people, vehicles, or any other obstacles may appear close to the route at any time. So for us, autonomous motion was not only about following a path, it was also about making clear, safe, and auditable decisions when an obstacle appears. So to achieve this, the software was integrated with 𝗏𝗏𝗃, with sensor topics, and a DDS bus interface to the virtual environment. This is important because it means that the control logic is transferable and can later be moved to larger mining vehicles. Regarding the navigation stack, the logic is closed loop, which means that the vehicle continuously senses the environment, understands where it is, plans its motions, and checks safety constraints, and then sends commands to the vehicle. So the whole process starts from the sensors. We used LiDAR and cameras. We used LiDAR LiveVox 360-degree LiDAR and a 2D SF45B LiDAR, a GoPro camera, and a RealSense stereo camera, and of course odometry feedback. These data streams were handled through specific channels, and the system performs two things, localization and SLAM, so the vehicle can understand its position in the underground environment. After that, the algorithm is used for path planning. We used nav2 and trajectory execution. But planning alone is not enough. A very important component is also the safety supervisor. The layer continuously checks if the planned motion is safe. Only after this safety check, we send spin and steering commands through DDS control to the vehicle. At the vehicle layer, the virtual layer receives the commands and also returns live feedback. So the message here is that our objective was not only to make the vehicle move autonomously, but to make sure that planning does not override safety. Regarding the distance-aware safety logic, the safety logic is very simple, very deterministic, and easy to test in our pilot. The idea is very straightforward. The system continuously checks the distance to the nearest detected obstacle. Then, based on that distance, it selects one of three speed states. If there is no obstacle within 20 meters, the vehicle can move at its maximum speed. Of course, it is adjustable. In our case, it was 15 kilometers per hour. If an obstacle is detected within 20 meters, the vehicle automatically switches to slow mode and reduces speed to 5 kilometers per hour. And finally, if the object is closer than 10 meters, the vehicle stops immediately. the logic is very valuable because it is transparent. It is not a black box. It gives us a clear and auditable, safe response. Regarding testing before testing on the real platform, we followed the simulation-first approach. This was very important because it allowed us to validate the navigation stack safely and efficiently before going underground. First, we created a representative mine tunnel geometry in Blender. Then we imported the environment and the vehicle model in Gazebo. And inside the simulated environment, we used nav2 to validate path planning and trajectory execution. We also injected virtual obstacles in order to test how the algorithm reacts. In this way, we verified the slow mode and the stop behavior before physical deployment. Of course, this gave us also a lot of advantages regarding integration risk, regarding faster iteration, and it helped us confirm the emergency stop logic early before moving to the real pilot in 𝗵𝗏𝗃. Another major part of the work was perception, especially person and vehicle detection. Initially, generic object detection with a YOLO algorithm was used, but of course this was not good enough for underground mining conditions. The reason is that mines have low light, difficult visual conditions, reflective surfaces, workers wearing specific uniforms, helmets, boots, so a generic baseline model did not perform as well as needed. To address this, we adapted and retrained the YOLO-based perception model using mine-relevant data. This improved the ability of the system to detect and localize people under underground conditions. This was very important because the output of the perception module feeds directly into the safety supervisor. In other words, person detection is not just for visual awareness, it directly affects vehicle behavior. If a person or an obstacle is detected, the system can automatically move from cruise mode to slow mode or to full stop. Finally, we had the integration with the 𝗙𝗏𝗃, DDS commands and fail-safe control. So after validating the navigation and perception components, the next step was full integration with 𝗙𝗏𝗃. We connected directly to the DDS bus. Through this connection, the controller could send commands and also receive live platform feedback. The control loop operated at 20 Hz. These commands were sent to the vehicle, were actually speed in meters per second and articulation angle in degrees. So at the same time, the platform returned live feedback, including joint angle, odometry-based speed, and an error bit. And finally, the final validation took place in a real mining environment at the 𝗵𝗏𝗃 mine in northern Sweden on 9 of March 2026. The pilot was the most important demonstration step because it confirmed that the integrated platform worked in real underground conditions. During the pilot, the 𝗙𝗏𝗃 vehicle operated with full autonomy stack. This included the nav2-based route execution, YOLO-based perception, and the speed envelope safety logic. This is a demo from the actual pilot in 𝗵𝗏𝗃. So as you can see in the video, this is the vehicle platform that was developed entirely from scratch from University of Lillea. It was equipped, as you can see in the video, with a LiveVox LiDAR sensor, a depth camera, a GoPro camera, and a to-do lidar. For safety reasons, you can see, because there were a lot of things inside the mine, of course, the autonomous navigation algorithm allowing the vehicle to move safely. As you can see here in the computer, you can see the humans identified, you can see the percentage, and you can see also the meters so that the vehicle can slow down or stop. So this is it, autonomous navigation inside the 𝗵𝗏𝗃 mine. You can see how it can navigate at the same time with a 3D LiDAR. We can have a 3D representation. Here we had some tests. You can see also the light on the head. So the vehicle stopped completely to ensure safe operation. Now it is 15 meters, so it started in a slow mode navigating, and again, after the obstacles disappear or reappear, it stops. So we had all this perception, classification, navigation, and at the same time, what we managed to do after this was a 3D representation of the whole mine. So as you can see, SLAM was deployed for real-time localization and mapping, enabling the full 3D representation, the 3D mesh of the underground environment, so that you can know, first of all, have a 3D representation of the mine and know the exact position in the mine in a 3D or 2D environment. It is in different modes, as you can see. We can have the texture, we can have the clay, and in the final mode, we have the full 3D representation as it is. The platform was capable of recording the environment and everything so that it can be reused later. And before going on, as we have already loaded, this is also the actual 3D representation of the mine, as you can see it, and as it is integrated with the whole platform. So this is it. Thank you very much.
Yes, here. Let me present. So our next presenter is Dr. Paula Lima. She's a marine biologist with a strong focus on aquaculture and marine robotics. She combines academic and industry experience and currently works at INESTEC, where she connects research and industry in marine science and technology. Paula?
Hi, good morning. So I'm from INESTEC, and I'm here to present the Portuguese use case where we tested technology for water-flooded mines. The Portuguese test site has two test sites. It's 𝗵𝗶𝗴𝗵 open pit mine, where we deployed the muon telescope. And for this we used our 𝗍𝗲 AUV. It's a hybrid AUV. It can work tethered or untethered, depending on what we want. And we use it to deploy the muon telescope. The other test site is a 𝗷𝗫𝗍𝗔 mine. It's a different kind of mine. It has 6 vertical shafts, and we had already done some missions there previously. For this, we used our 𝗍𝗀 Neo underwater explorer, and also we developed for MineEO a cage so that we could enhance the autonomy of the robot and also minimize the risk of deployment. Regarding 𝗵𝗶𝗴𝗵, as I said before, we deployed the telescope, the muon telescope that was developed by our partners from Vigner. And for this, we needed to build transport squid for the muon telescope and develop new algorithms. Previous to going to the test site, we did some tests in a simulation environment where we developed the algorithms, and then we tested these algorithms in our test tank in the lab, and also we went to a marine basin to test all the setup. Then we went to the 𝗵𝗶𝗴𝗵 test site and we deployed the muon telescope after we did some bathymetry to check exactly where we were going to deploy it. 72 hours later, we did another bathymetry to check where the muon telescope was, and we collected using the 𝗂𝗲𝗵𝗶𝗃𝗀𝗵 AUV with the help of the April tags that were fixed on the transport squid, and then we sent all the data to our partners for processing. Regarding the 𝗷𝗫𝗄𝗁, we needed to develop, as I said before, a cage, and we did some upgrading of the robot, namely on the batteries. And unfortunately, we couldn't go to the 𝗷𝗫𝗄𝗁 to do the tests due to the safety of the robot, and the mine wasn't in very good conditions when we got there, so we couldn't do it. So we decided to simulate the mine. Since we did some missions some years ago, we had some data. And here in the first video, you can see the robot in the simulation environment without any input of data, so it was collecting the data through the... I'm going to pass the videos so that we don't stay here very long. So you can see that it is doing a 3D mapping of the mine. And then he did a second mission using the data he already collected in the first one and increasing 25 meters more. So I forgot to say that the cage has an optical modem, so the robot can do the mission untethered and then return to the cage and transfer the data to the cage, and the data has a tether that we can see and collect all the data collected from the robots. I'm trying to go faster with the video, so this would happen in real life if it was possible. Okay, why doesn't this stop? Why doesn't this go? I only have one more slide, but this... okay, sorry. Looking at you. So this is the result the data after processing. We obtained this mesh, and this is the 𝗷𝗫𝗄𝗁 mine map. Okay, thank you.